In this video, we focus on the background section of the introduction chapter. Numerical methods are techniques that allow us to solve mathematical problems. Now, the keyword here is that we have quantitative solutions to numerical problems. So the outcome of these numerical methods will be a number or a large set of numbers, not a abstract mathematical object. No, with numerical methods, the outcome that we will have is numerical, are numbers. They allow us to solve problems, solve mathematical problems which are too difficult or even impossible to solve in an analytical way. Moreover, they allow us to perform virtual experiments which are either too hard, too expensive, or even unethical to do in reality. They are always approximate or very rarely exact. So there are always errors and approximations that are present in these numerical solutions. But it is important to note that they can be very accurate. Although this is a relatively new field of mathematics, numerical mathematics, it already has quite a rich and long tradition, but remains very alive and very topical to date. Even though computational science and numerical simulation is something that we tend to think of as something very modern, all of the numerical methods that are being used today in the field would not have existed if it were not for a number of prominent mathematicians from the past. And here I compiled a short list of some of the most pioneering figures in the field. And we see some very well-sounding names. For instance, we have Isaac Newton, who gave his name to Newton's method, and Newton's method is one of the most performant methods for solving nonlinear equations in a very, very fast manner. And more on that will come in one of the subsequent lectures. We have Leonhard Euler, who came up with Euler's method. Now, Euler's method is still the most fundamental and basic way of solving ordinary differential equations in a numerical way. So also a very important method is Euler's method for differential equations. We have Carl Friedrich Gauss, who devised the Gaussian elimination method, which is the standard way of solving linear systems, not only by hand, but also in a computer. There's Louis Richardson, who came up with the idea of Richardson extrapolation, but also was one of the first persons, let's say the first person, to attempt a numerical computation of the weather in already the 19th century. So this was well before the advent of the electronic computer in the 1940s. And also more recently, we have John von Neumann, who also has various contributions to the field of numerical mathematics, who is also a very prominent figure there. Now let's take a look at the kind of problems that we can solve today using scientific computing and numerical methods. So one of the things that we all benefit from today is weather forecasting. Now, for weather forecasting, we solve a very large number of differential equations on a very large computer, and the output will be the wind velocities, the precipitation, the humidity on all different kind of places among the world. So for this, we need numerical methods, and this is one of the key applications of numerical methods that touches everyone's daily lives. But also other application areas, for instance, drug discovery, where from a certain protein chain or a certain chemical compound, we want to find the geometrical configuration which has the lowest energy. And this is a very computationally expensive process, trying to find how these protein chains are folded together. This also requires an enormous amount of computational power. and is very relevant for instance, drug discovery. And this specific picture is from the Folding at Home project, which is kind of a crowdsourcing project where people can use their computers at home to provide computational power for researchers which are in dire need of computational power every day in order to solve these very relevant problems in a numerical way. Another application area which is close to my research expertise is renewable energy. Now, in renewable energy, for instance, here we have an array of wind turbines shown by the gray disks over here, and they impact each other through their wakes. So they negatively impact the downstream turbines and cause a reduction of the power extraction in those downstream rows. Now, in order to be able to model that or to control that in reality, we need accurate numerical models to kind of predict the effects of the wind, the effects of a wind direction change, the effects of a turbine setting change on the overall output of the wind farm. And for this, we use a computational fluid dynamics, also a very highly demanding computational application to solve these kinds of problems as well. But also in aeronautics and astronautics, numerical computations are very, very important as they start replacing wind tunnel testing more and more. So this allows a relatively inexpensive alternative to wind tunnel testing. For instance, here showcased by this simulation of a rocket booster by NASA. So these are just a small set of applications that all require very advanced and very performant numerical methods, which all have a very important and relevant impact on daily society. It is important to remark that not only do very complex and involved applications require numerical methods, but also for relatively simple problems, it quite often happens that analytical solutions do not exist, and numerical methods are your only viable solution for solving the problem. And an example that we will be looking at right now is the damped pendulum. Now, the damped pendulum consists of the following situation. We have a mass, a point mass with mass m, which is suspended by a rigid rod of length L to a hinge. At a time t equals 0, we take our point mass and we simply drop it and then try to track where the location of this mass is as a function of time. So we will try to cast this into a mathematical problem and then try to solve it using numerical and approximate analytical solution methods. So in order to do this, well, we are looking at the mechanics of a point mass, and for this, well, we need to go to the governing equations of mechanics, and we tend to start with the Newton's second law, which dictates that the sum of the forces on this mass is equal to the mass times its acceleration. Now, in this specific case, well, we can look at a free body diagram on the left, which indicates the different forces which are acting upon our point mass. So we have gravity pointing downwards. We have a drag force, which kind of represents the damping of the motion of the pendulum, for instance, by aerodynamic drag. And we have the tension force of the rod. Without this tension force, the mass would just fly off. So we have a tension force which keeps the ball attached to the rod. So those are the three forces. And we can take a look at the accelerations. Now the acceleration, we have one acceleration, the centripetal acceleration, which points towards the center of rotation, so towards the hinge, which can be written as mass times the acceleration in the normal direction is equal to the tangential velocity squared times L. And we have the acceleration in the tangential direction, which is proportional to the second derivative of the angle theta. So we know that the tangential velocity Vt is equal to L times the time rate of change of the angle. So that's L times the derivative of theta with respect to t. And then simply by differentiating this with respect to t, we can derive this expression, namely that the tangential acceleration is equal to the length of the rod times the second derivative of this angle theta with respect to t. Now, we're mostly interested in the tangential movement of the mass, because the normal movement, well, that's completely constrained by the bar, and we're going to look into the tangential movement only. Now, in order to do this, well, we can project all these terms up onto the tangential vector, so all onto this plane, and then we end up with the dynamics equation for the tangential direction. And we see here three terms. So we have the first term, which is a damping term. So the minus sign comes from the fact that this force is aligned with the negative of the tangential velocity itself. So we have minus CL times d theta dt. We have this downward pointing force, which after projection becomes minus mg sine of theta. And then we have the right hand side, which is mass times tangential acceleration, is ml times the second derivative of theta with respect to t. Now, if we try to solve this problem, this damped pendulum problem, well, we need to provide some initial conditions. So we have our pendulum dynamics, which we derived in the previous slide. And we have to provide some initial conditions. So namely, so this is a second order differential equation. So we have to provide two initial conditions. The initial position of the mass, so the angle theta at time equals 0, which we just parameterize here as theta 0. So that can be, for instance, 45 degrees or 90 degrees if you hold the pendulum horizontally at the initial stage. So that's a parameter. And we also have to provide the initial velocity, the initial rate of change of theta with respect to time is also a initial condition. And here we just set it to 0, which means that at the initial stage, the mass is at rest, and we just drop it and take a look at how this evolves in time. Now, looking at this initial value problem, well, this is a second order nonlinear ordinary differential equation, and the bad news is that this cannot be solved analytically. Why not? Well, we have this, if this were a linear second order ODE, well, that's no problem at all, because there are methods with which we can solve them. And if you don't know them, then I would suggest you look into chapter 2. But for a nonlinear equation, this is in general not the case. And more specifically here, this is nonlinear because of this term over here. So this sine of theta is a nonlinear function, which renders this initial value problem impossible to solve by hand. However, fortunately, we can try to solve this initial value problem numerically, and that doesn't tend to be so much of a problem. Actually, you can code this up. So after you've finished all the video lectures up until the last chapter where we discuss ordinary differential equations, coding up this into a numerical program should be no issue at all for you. And here we look at how the behavior of the pendulum is after we solve this system with one of MATLAB's go-to solvers for ordinary differential equations, which is ODE 4.5. The 4.5 stands for the order of accuracy of the methods, which is between fourth and fifth order. But more on that will come later. Now, what do we see here? Well, on the left, I plot the pendulum, and we see that at the initial stage, the pendulum is horizontal. So in this case, theta naught is equal to pi over 2, which is approximately 1.5 something. And we will see this is a movie, and when I play it, we will see the movement of the pendulum on the left. And on the right, we see the solution to this equation. So that is the angle theta that this pendulum makes with the vertical axis as a function of time. So if I play this, well, we see kind of a very physically intuitive behavior. We see that this is a damped pendulum motion, so the pendulum moves from left to right, and because of this damping force, the amplitude of the movement goes down as a function of time. So we see that this kind of up and down movement is damped, so the peaks are getting flattened out, and this will, if we let this keep on running until eternity, the pendulum will come to a halt at the bottom position. So that is how we solve this numerically. Now, some of you might say, well, I know how to solve this analytically, or I know how I can solve this analytically in certain cases at least, because we can linearize this nonlinear ordinary differential equation. And we will do this by saying that, or making the observation that for small angles theta, the sine of theta is approximately equal to theta itself. Now, this might come off as something that we just grab out of thin air, but if you actually write out the Taylor series for sine of theta close to 0, then you see that this is the leading term that pops up there, and that it is completely valid to say that for small angles theta, the sine of theta will be approximately theta. Now, if we do that, well, then we can rewrite this nonlinear equation. So we can rewrite this nonlinear equation into a linear second order ordinary differential equation. And that is something that can be solved analytically with relative ease. If you don't know how to do this, well, again, I would refer you to chapter 2. It's not that hard by itself. So the idea is that you solve this characteristic equation, which will give you roots to this characteristic equation. So this is a certain number which depends on parameters such as C, L, and M. And then the solution to this linear ordinary differential equation can simply be written from a combination of exponential functions. So by making this approximation, we were able to linearize the nonlinear ordinary differential equation that could not be solved analytically to a linear ODE that we can solve analytically. Now let's take a look at how these solutions actually look like, and if we compare them to the nonlinear numerical solution of the nonlinear problem. And we see that for small angles, so if we start out our simulation with a small angle, so theta naught equal to 10 degrees, we have here a plot where the orange line is the analytical solution and the blue line is the numerical solution that we obtained from MATLAB. Now on the top view here, we see that for small initial angles of 10 degrees, that these two are virtually indistinguishable. So this means that for small angles, well, this approximation is very valid. and we can analytically solve this problem. But we see that once we start with a larger initial deviation, a larger initial angle, that, well, the analytical solution and the numerical solution, they deviate a lot from each other. And after a certain amount of times, well, they both have somewhat similar qualitative behavior. But we see that, for instance, the numerical solution, which at this point we is our only reference to the true solution, we see here that, for instance, this numerical reference solution in blue is in antiphase with the analytical solution. Sure, this is quite disastrous, and for this case, the assumptions that we made in the analytical solution is not valid because 90 degrees is definitely not close to zero. And in cases like this, well, analytics will get you nowhere, as this is shown over here. Analytical solutions completely disagree with reality. So in those kinds of cases, numerical solutions are actually all you have in order to solve your problem. However, numerical solutions are not perfect, and there are certain issues that pop up when we look at numerical solutions, which can be non-physical. So let's take a look at this case over here, where we are solving our nonlinear pendulum problem, and we have as initial condition that the initial angle is equal to pi. So the pendulum is standing up straight, which is in equilibrium. So if we look at the equation over here for these initial conditions, we see that, well, this gravity term, this is the sine of pi, which is equal to 0, while the initial velocity, this initial rate of change of theta from this initial condition is also equal to 0. So actually we can see that we can solve this problem because there are no driving terms in this equation. Theta should not change and should forever remain equal to pi. So, and also intuitively, if we set such a pendulum in a perfectly upright position where there are no perturbations from, let's say, wind or vibration, then this is in equilibrium. It should remain upright forever. However, if we take a look at such a numerical simulation, we see that initially this is the case. So we see that theta does not go away from the initial position, but after a while something happens and it actually falls down. Since there is no real physical perturbations over here, there is not really a physical reason why this would happen. And the actual reason why this is happening is because of rounding errors. Because this term on the right here, which analytically should evaluate to 0, is not exactly equal to 0 if we evaluate it using a computer. Why that is something that will pop up in later within this video lecture. So that is rounding error and some unphysical behavior that we obtain when we observe the solution in that way. Now, another physical unintuitive solution is if we take a look, for instance, here, we start the pendulum not completely upright, but very close to it. So this is 95% of pi. So I put the pendulum close to an upright position, but not exactly upright. Still, the initial rate of change of theta is 0. So this means that this mass is at rest at time equals to 0, and then we just let it fall. Now, from physics, from basic Newtonian mechanics, we already know what would happen. So note that we turned off the damping. So we turned off the aerodynamic damping. So at this point, this term drops out, and this becomes an undamped pendulum. Now, such an undamped pendulum will have conservation of energy. So this means that at this point, all the energy in the system is potential energy. After which, when we let this mass loose, it will drop, convert its potential energy into kinetic energy, convert its kinetic energy back into potential energy, and stop again at the exact same height that it reached in the initial condition. After this, it will again drop, convert potential to kinetic energy, and reach the same initial position as it did at the beginning again. So this should lead to a completely periodic solution, where at every period the mass swings, not a full circle, but almost a full circle, until it reaches the exact same height as it did before. Note that it can never reach this upright position, because in the upright position, the total energy in the system would be larger than it was in the beginning. And our equations, they clearly state that there is no input of energy in the system. So let's take a look what happens if we solve this system numerically. And we see initially, well, we can observe the behavior that we predicted. But after a few oscillations, well, we see something weird happening. So we see that the amplitude of this oscillation gets larger and larger, and eventually we even have swing over of the pendulum over the top. So this means that somehow this numerical solution attained additional energy. So in that sense, this numerical solution, or the behavior of this pendulum, is not energy conservative. So that is definitely an issue that we have to take into account, which is non-physical. So we have to be careful of numerical solutions in certain cases. Another example, let's say we have a pendulum, and again, well, we drop out the damping terms. So this second term here is gone. The initial condition is that we have a horizontal pendulum, so theta at time equals 0 is equal to pi. And we have the initial rate of change of theta, so the derivative of theta at time is equal to 0. So we just have a mass at rest in a horizontal position, after which we let it fall. Now, in all the previous results, for the numerical results, we use this ODE45 integrator, which is the MATLAB high order, high accuracy go-to integrator. An alternative is this ODE323 integrator, so that's another function that we have in MATLAB available, which has a bit lower accuracy but tends to be much faster than the ODE45. Now let's take a look what happens in this case. So we see that they start from the same initial condition. The ODE45 will be drawn in blue. The ODE23 will be drawn in orange. And so we see that initially these solutions are virtually the same, virtually indistinguishable. However, as time progresses, we see that clearly the blue and the orange pendulum start deviating from one another. And at the end of this time horizon, we already have really a quite significant phase lag between these two time integrators, which are both considered to be relatively accurate. So this does show us, well, that different numerical solutions, they can be very different from each other. And in this case, it's even not clear which would be the actual true solution to this system. So in order to kind of wrap up this background on the introduction, well, we introduced what numerical methods are here. So they are techniques for quantitative solutions to mathematical problems that are too difficult or even impossible to solve analytically. They allow us to do virtual experiments, which may be too hard or expensive to do in the field. And we looked at some well, some state-of-the-art examples and applications, for instance, weather forecasting or drug discovery for numerical methods. Now, also for much simpler applications, for instance, this damped pendulum motion, we've actually seen that it can easily occur that there are no analytical solutions available. We solved the problem using numerical methods, but we did find that numerical errors can occur. We did find that maybe different numerical methods give different solutions, and it's far from trivial at actually saying which would be the actual real solution or the actual accurate solution. So the main conclusion that I would like to give in this video is that numerical results, although they are quite often very accurate and very valuable, should always be interpreted with care. Now, within this course, we will provide you with background knowledge on the numerical methods that are being used to calculate these solutions, and that should allow you to make informed decisions on whether numerical solutions are accurate and trustworthy or not.